event. So we're going to update the estimated noise values from that first pass result. We see these numbers are now different, the baseline and event noise. We can erase the previous results if we have any from our second analysis, which we don't, and we can do a second pass to locate the event again. That helps us improve the results that we get from our first pass. So now we're going to wait. While we're waiting, I can just comment that R-OTE, typically the menus typically progress from the top to the bottom. So as we entered our search values, we got our maximum event durations. We could have input those manually too. Our mag drops, then we would, if there were some results from a previous analysis, we could erase those. Then we do our first pass. After the first pass, we check these estimated noise levels and update those. If we've had a previous analysis, we can erase those, and then we would do our second pass. That's where we are right now. We're waiting for our second pass. Notice that my progress bar has disappeared, so just toggle it to the front. We're at 80%, progressing well. Typically the second pass seems to go a little faster than the first pass. Just about done. Now the progress bar has disappeared. We need to wait until we see that the RStudio console reports that we're done with our analysis, which we see with a ... done. And now the results that we've produced in our Google Chrome window are complete. We see the D frame time reported, the R frame time reported. We have some likelihood weighted results, and these are a range of frame numbers that are possible, but not the maximum likelihood results. We have the minimum and maximum frame numbers reported that are the minimum and maximum for the disappearance. We have the minimum maximum for the reappearance. We have the maximum likelihood D and R. We have the duration in frames. We have the baseline noise, the event bottom noise, and the computed mag drop. Then we produce from the frame numbers, we can, and from the timestamp and our time delta, we can create the actual event time and universal time, and that is produced at the end of this line. 2015 9/10 11/08 07.73 was the disappearance, and the R was the 2015 09 10 at 11:08 19.709. The duration is 359 readings. The duration in seconds is 11.97, which is less than our maximum predicted. We have our baseline noise, our event bottom noise, and our mag drop, which is a lot less than the 0.2 predicted. Not unusual. A nominal mag drop of 0.08, a maximum mag drop of 0.09, and a minimum of 0.7. When we report out our results, we'll be reporting out the DNR times. We'll be reporting out the signal to noise ratio, and we'll be reporting the error bars, which we haven't computed yet. I want to show that for such a noisy light curve, we have a range of values. The maximum likelihood is shown as the red curve, and I can zoom in on this a little bit so you can see it a better. So the maximum likelihood event is the red curve. The green curves are the range of other possible events that we could have picked based on the noise involved and the mag drop and the possible start and disappearance and reappearance times. And those green bars come from a whole number of relative likelihood solutions for the event. Now the maximum likelihood has a relative likelihood of 1, but we have other possible solutions. Instead of 1948 for the disappearance, it could be 1949 that has a relative likelihood of 0.69 of the best event. And on down, there's a lot of different possible events, and R-OTE lists all of those clear down to a relative likelihood of 0.05. So what we're seeing is that when we have a very noisy event, we're not 100% sure that the disappearance isn't a little bit later, or excuse me, the disappearance isn't a little bit later or a little bit earlier, or that the reappearance isn't a little bit earlier or a little bit later. R-OTE gives us the maximum likelihood event, and that's what we would end up reporting. Now, we want to produce the error bars for this observation. So the first thing we have to do, dropping through our menu, is analyze the baseline noise. And R-OTE gives us a plot of all of the baseline noise data points. It does a Pearson's R correlation of the data point versus the adjacent data point next to it. Is there a correlation? And if there's a large correlation, R-OTE notes that down here in the correlated factors plot. We see that there isn't a lot of correlation. If there is, you'd see more data points indicated in a lag that typically is a result of scintillation. If there's a lot of scintillation or some other thing that causes the light curve to vary kind of sinusoidally, or varies in large blocks of fluctuations, then we'll see a lot of correlation in adjacent data points. This one has low correlation. We're fairly good on our noise analysis. I'll click this down. And then the next stage would be to calculate error bars. So our next menu that pops up says that it automatically transfers from our noise analysis, our B, our A, our sigma B, our sigma A, and it automatically transfers the noise coefficients, our auto correlation coefficients from our noise analysis. So those are all filled in for us. We're now going to run a Monte Carlo simulation of our square wave, our idealized square wave for the detection, the maximum likelihood detection. And we're going to add noise using the same noise from the event with the same correlation coefficients for the correlated noise, and we're going to add that noise to the idealized light curve 100,000 times, and then we're going to resolve for an event and see if that the noise from the event actually could have changed our solution, and if so, by how much. To do that, we want to calculate the edge histogram and do an error bar plot. That's our next step. We see a progress bar pops up, and this progress bar is going to take quite a while because it's a very long data set, and we have a lot of noise in our data, and it's going to take 100,000 iterations of that Monte Carlo solution to come up with our analysis and our histogram. So we're going to wait a little while. While we're waiting, I'll just run through some further discussion on what we're doing. So we're going to produce error bars for 3 different confidence intervals: 0.06821, 0.095, and 0.09973. Now, occultation error bars we have found from research that Bob Anderson has done, are a non-parametric distribution. That is, if you plot the histogram of error bars produced from 100,000 Monte Carlo solutions, the histogram does not fit any normal or other type of distribution. It doesn't fit a normal distribution. It doesn't fit a log normal distribution. It doesn't fit a student t distribution. There's no distribution that fits the histogram that we produce by our error bar analysis. As a result, we can't actually say that the confidence intervals match a 1 sigma or 2 sigma or 3 sigma value as indicated in this text, because the distribution is not Gaussian, it's non-parametric, and we can only report out that the confidence interval is equivalent to a 1 sigma distribution if the distribution was Gaussian, but it's not, and we can only report out the actual confidence level for the 3 confidence levels that we analyze. Okay, well, we're 40% done, and we're waiting. So while we're waiting, I'm going to clean up some things here. I'm going to go back to my folder. So one thing I want to show you, this is, I showed you that we started out with a path map file. We started out with a CSV file. and we started out with a Excel report file. But notice that our folder now has an R-OTE CSV file, which has a different format than the original iMovie CSV file. It's much abbreviated, simplified, with the timestamps included in brackets. I did a noise analysis, and we now have two noise analysis files, one in PNG format and one in PDF format. Both are preserved. The formats are a matter of preference, and whichever you find easiest to record and use. Remember, we did a timestamp analysis in our CSV file. We found 0 errors. That plot is recorded in our file as well. So as we go through our different analyses, we can preserve and save several of these reports that we're producing. Okay, let's see how we're doing on our progress. We're about 80% done. Let's click this down. So there's some other boxes here as we go through. We can, when we get some histograms printed out, we can actually change the characteristics of those histograms with these toggle switches, and we can put in an extension, some additional text if we want to qualify the histogram title. For example, we can input some additional text and append that to the file that produces the histogram. We can superimpose a normal distribution of best fit to the histogram, and if we change any of these, we can do an error bar plot and report, and that will generally go a lot quicker because we've already done the analysis. And the last button is a shortcut to go back to locate the square wave event. So we're just about done. Okay, so R-OTE has completed our noise analysis.